Okay, welcome back here at this global virtual lecture hall. I'm glad to see you all here. So maybe we will make a very short round of welcome to see if everybody is connected. So Beijing, hello Beijing. Are you there?
Hello. Yeah.
Okay, so Beijing, good evening. I think it's also evening in Beijing, right? It's,
yes.
What time is it?
It's early evening. Almost.
Okay, thank you. So, Warsaw, good morning, I guess. Hello. In Warsaw, right? Yes.
Morning, Warsaw, 9:15 in the morning.
9 o'clock in the morning, okay. Past 9 in the morning. And Zurich, Simon?
Hey, good morning, Rolf.
Okay, so the connection to Zurich also works? Yes, glad to see you all back. And Munich?
Good morning, Rolf. Here is Munich. It's also 9:15 here.
Okay. Okay, so the connection seems to be working? Right. Okay. So maybe we can now switch back to Tokyo. I would especially actually like to welcome back the people from Warsaw who had their national holiday last week. So I have, because this is an experiment, as we said at the beginning, I have a few preliminary remarks. One is that we have been asked, and there has been a discussion on the forum, about the book publication and whether there would be electronic versions. We now have permission from MIT Press to publish a few chapters, so we will publish some of the core chapters of this course in electronic format, chapters 3, 4, 8, and 10, and they will be available sometime this week in I guess, PDF form. In addition, MIT Press has volunteered to send a few copies of the book to each site, so maybe you can also circulate these copies among the students. I hope that helps to solve the problem a little bit. Now, concerning the video conferencing system, this is also an experiment. We're always trying to optimize things. I mean, one of the things that people complained is that I'm not looking at them. Now, the problem was that in the previous setting, the camera in Tokyo was on the side of the auditorium. When I was looking at the camera, then I would not look at the audience in Tokyo. And when I looked at the audience in Tokyo, I did not look at the camera. So now we solved the problem in that we put the camera in the center of the auditorium here in Tokyo so that I can look at all audiences at the same time, if you like. Then there was a lot of variation in the sound levels last week. We solved that in that we now have a head-mounted microphone that maintains the same distance to the mouth at all times. And then I'm happy to say that we now have well over 600 registration on the website, and I would encourage everybody to register on the website. Also, if you want to download the PDF versions of these chapters, then you have to register on the website. Moreover, there was a discussion, or someone raised the problem of the church touring thesis that I mentioned last time in the forum. Indeed, there is a lot of confusion around about the church touring thesis in the literature, and we're at the moment in the process of trying to resolve the confusion that's actually around this problem. And we'll get back to you in a couple of weeks. Okay, last comment that I have is, if you like, you can do the exercises. For the students in Zurich, this is compulsory if they want to get credit. It may also be an idea for you, if you don't need credit to do the exercises. There are two types of exercises. One that we call open discussion problems, and the other that we call task sheets. Now, the open discussion problems are just interesting problems to think about. and they're relatively open. Now, because we have over 100 students in Zurich taking the course for credit, we cannot mark 100 essays every week. And so we have these task sheets, which are more restricted questions, sometimes multiple choice, but sometimes you just have to list keywords, and they have to be handed in. But if you're only interested in interesting discussions, then please have a look at the open discussion problem sheets. Okay, I would recommend that. So now today we have the third series of these problems for you to look at. Okay, here is I mentioned that we have always a bit of news items at the beginning, and what you see here is there's a German magazine, CT, which is one of the largest PC magazines in Germany, and they have, you recognize the website here, of the lectures, and so they have a feature about these worldwide lectures here. Okay, now I would like to ask all the sites, are there any questions from the various sites about last week? You can either ask them now, you can ask them on the forum for everybody, or you can ask them during the break. Are there any questions right now? I can't really see anybody waving, so please ask your questions, at any time, especially also during the break or on the forum. Okay. Now this was what we did last week. So I expect you to have read chapters 2 and 3. Chapter 3 will also be available electronically. And exercise 2 is in order to familiarize yourself with the basic ideas. So I expect people to have done that already. Now we have a special assignment for Munich, which is a short presentation on the frame problem. I would now, let's see. Okay, here is Denet's view. That is also, you can also find in the book. And I would now like to switch to Munich for a short presentation of the frame problem. So I guess they will now take over also the application sharing.
Good morning, Rolf. We have a presentation by 3 students, Max, Andy and Helmut, and they will each give a short presentation on aspects of the frame problem. Here is Max.
Okay. Welcome, Max, Andy and Helmut.
Good morning.
So you have the floor.
So,
maybe we can switch. Yeah. Okay.
The next following 10 minutes, we'll try to explain one of the famous and fundamental problems of AI, the so-called frame problem.
Can you adjust the sound level is relatively, we don't understand it. Can you adjust the sound level, please?
Sprich mal.
Can you hear me?
Oh, now it's much
Hello?
better. Yeah. Yeah, now it's much better. Yeah. Okay, thanks.
So, in the next following 10 minutes, we try to explain you one of the most important fundamental problems of classical AI, the so-called frame problem. It was the first time mentioned by McCarthy and Hayes in 1969 and caused a lot of interest in the last few years. I think that most of you have already read the book of Professor Pfeifer, so I will just give the short outline of the example given by Dennis C. Dennett. Okay, let's start. Once upon a time, there was a robot called R1. Its only task was to fend for itself. One day, it decided to arrange for it to learn that its spare battery, its precious energy supply, was locked in a room with the time bomb set to go off soon. The R1 located the room and the key to the door, so okay, yeah. There's a slide. Okay, I want to locate the room and the key to the door and formulate the plan action which calls pull out wagon room would result in the battery removed out of the room. Straight away active. Unfortunately, however, the bomb was also on the wagon, and R1 knew that. But he didn't realize that pulling the wagon would bring the bomb also out with the battery. So, okay, I've got the next micro. You understand me better now?
Well, this is
okay.
Much better, yeah.
Much better, thank you very much.
Okay, good. Shall I start once more? Or? No. Okay, so the bomb went off and R1 missed his action. So back to the drawing board. The solution is obvious, said the designers. Our next robot must be made to recognize not just the intended implication of its acts, but also the implications about their side effects. They called their next model the R1D1, the robot deducer. They placed R1D1 in the same situation like R1, and as a 2, it hit upon the idea of pull-out, wagon, room. It began as designed to consider the implication of such a course of action, and it had just finished deducing that pulling out the wagon would not change the color of the room's walls, and pulling out the wagon would cause its wheels to turn more revolutions than there were wheels on the wagon when the bomb went off. So, back to the drawing board. We must teach it the difference between relevant and irrelevant implications, said the designers, and teach it to ignore the irrelevant ones. So they developed, a method of tagging implications as either relevant or irrelevant to the project on the hand, and installed the method in the new model called R2D1, the robot relevant deducer. When they now subjected R2D1 to the test, they were surprised to see it sitting down, Hamlet-like, from Shakespeare, containing the ticking bomb. They said, "Come on, do something," shouted the designers. "And it's still working," he retorted. "I'm busily ignoring some thousands of implications I have determined to be irrelevant. Just as soon as I find an irrelevant implication, I put it on the list of those I must ignore," and the bomb went off. So, let us now summarize the essential points of Dennis' example. R1 has the problem of determining the implications of an action. It doesn't realize that moving out the wagon will also have the side effect that the bomb will also moving, because it lays on the wagon. The robot obviously doesn't know that this is relevant. R1D1 tries to consider all potential side effects which could happen. These are a lot, you can imagine. And R2D1 tries to consider all irrelevant side effects. So, there's no advantage between the last two. Now according to Eric Chandler, the frame problem has two aspects. Our robots, R1, R1D1 and R2D1, were suffering from the prediction problem, which has to do something with determining what is relevant and what is irrelevant. The second problem is the qualification problem. It involves all the prediction which it involves the prediction under what an action can apply. So I will now give up because the time is running. Sorry.
Okay, here we will have Helmut with the second part of the talk.
Hello. I will present you some suggested solutions to the frame problem. For once, there's the so-called frames solution proposed by McCarthy and Heiss, which sees at the situation that most events in just affect local parts of the real world. So what they try to do is to segment the world into blocks, so that only the aspects, so that only local changes are made in a block. The problem with this approach is that if you have big blocks, you have still a lot of combinations, possible combinations of different events and changes of properties. And if you have a lot of small blocks, then some action can possibly go on further than block boundaries. So on the one hand, you have to still compute a lot of combinations. On the other hand, you have to compute a lot of blocks. So the thing that just moves the problem to another domain. Another possible solution, which was suggested by Minsky, Schank and Abelson, are the so-called scripts, which use the stereotype kind of thinking in real world or in humans. This approach was pretty successful, at least for very basic agents, like, for example, ant-like intelligence. But it looks kind of hardwired. The problem is that there's no learning in this approach. So the designer has to change the stereotypes of the system.
Excuse me, we should maybe kind of speed up a little. I mean,
yes, okay. Cheap test, sleeping dog. Cheap test just says something about eliminating as many possible facts, but test basically all possibilities. Sleeping dog is the strategy of not changing anything, but until there's a reason to do so. But the problem is how to find out the reason if you ignore everything. Okay, I'll finish here.
Okay, Rolf, Andy finally will wrap up the problem.
Okay, the next slide, please. Here. And the next thing we want to point out is why didn't the frame problem appear before 1969 and why is it so important for AI? So according to Dennett and Felician, that also Professor Pfeiffer, this is the book which also Professor Pfeiffer refers to, nobody before McCarthy and Heiss ever tried to implement an application that is dealing with a complex world. And so all we had about the frame problem or the problem of representation change was just a result of introspection and an analytic approach. When McCarthy and Heiss tried to do it, they were using a synthetic approach to the problem. Now they changed the point of view. There's camera, sorry. And so the problem for the first time crystallized. Now it became evident that it was really a profound and fundamental problem. And this is also very good evidence for the synthetic approach that it's really helpful and we can estimate even philosophical problems that were old and under a new point of view. Yes, I think that's enough. And to finish it, it was a little bit difficult for us to find out in our researches for the presentation. So we have a little question for Professor Pfeiffer. In how far does modern AI resolve the frame problem and it minimize its implications? Thank you.
Okay, well, thank you very much for this presentation of the frame problem. I think this was really the people in Munich, thanks very much. They really worked out the essence, I think, of the problem. Also, I would like to thank them for the question because, of course, the whole course that were the whole course. I have a small problem here with the smartboard. That's why I'm kind of interrupted. The whole course will be about how we can resolve. Maybe we will not be able to fully resolve. I think any system will always have, in some sense, a frame problem whenever we're dealing with the real world. But we will investigate to what extent we can come to grips with the frame problem. So I think you were really asking kind of the essential problems. I need some assistance here with the smartboard. Okay, so now we have a small problem with the application sharing. I just want to refer to today's topics. So the first thing that I will be doing is I will be presenting a case study on embodiment. I mean, the whole course is on embodied artificial intelligence, embodied cognitive science. So I would like to just get get some intuition across on embodiment. And then we have we finish up the fundamental problems of AI and cognitive science. So we already had the frame problem. I will talk about another one, which is a symbol grounding problem. That's a really the symbol grounding problem, which is a really difficult one, a really hard one. And finally, we start with embodied cognitive science, designing autonomous agents, to familiarize you with the synthetic methodology. And then we have Professor Inaba from the University of Tokyo, who will talk about the latest from Japan. Okay, so that's the program for today. And now, as soon as we have the application sharing running again, I will start with the case study on embodiment. So this is an experiment that we did. Yeah. Okay. I will start this. Okay. Thanks for Kano-san. Okay. Right. Let me just start here and see if everything works. Yes, everything works fine. Thank you. So we're getting, yeah. So today's topics here, I just listed that. We get the latest from Japan from Professor Inaba. And now I would like to present this case study in embodiment. Okay. This is an experiment that we did a couple of years ago in our laboratory. And imagine, so this is an arena which is filled. This arena is filled with more or less randomly distributed styrofoam cubes. And it's kind of very light material. And then we put a couple of robots into this arena. And these are very simple robots that we actually built together with students in one of the classes. Even this is very, as you know, it's very easy to build. We also had psychology students, philosophers who actually put together these robots. Now we just put them in there and we let them work. Now here's what happens. Now, so this between two frames takes about 4 minutes, 3 to 5 minutes. Another 3 to 5 minutes. Another one. Another one. And another one. So this is the overview. Now, what I would like to do is, what are these robots doing? Maybe the students here in Tokyo, have an idea. Just what do you think they're doing? We can have a look at this slide again. What do you think these robots are doing? I mean, if you want to describe that. Maybe we can have the second microphone, and maybe one of the students could give a comment on this. Dominique, you want to give it a try? Yep.
I think the robots can change the environment. So by himself. Okay.
Robots changes environment. I think this is an excellent comment. Robots change the environment.
Yeah. So by himself.
Yeah, because often in robotics, people only take into account the way the environment affects the robot, but not the way the robot affects the environment. Yes, I think it's a very good point. Thank you. Okay, do we have another? What are they doing? I mean, if you just look at what they're doing. Just look at what they're doing. Let me show you the picture. The other, it doesn't have to be, philosophically very deep. You just. Okay, let me give you a few suggestions. They're making clusters, huh? Making clusters. Okay, any other? Clusters. And then you could also say they're making free space. Right? You could say that they're making free space. So now they can move around better. Okay, any other suggestions? Other suggestions? Okay, I have one. They're cleaning up. They're cleaning up. Many parents with little children who like to play with Lego told me that they would like to have robots like that to clean up the Lego parts, right? So they're cleaning up, and this is also why these robots are sometimes called in the literature the Swiss robots, because the Swiss are known, to be very neat and tidy, and they like to clean up things, so they're called the Swiss robots. And I think in many respects, actually, the Japanese and the Swiss are very similar. The Japanese also like to clean up things, and so they could also be called the Japanese robots. Okay, well, anyhow, so what are they doing? Now, that's basically a description of what they're doing, but what we're really interested in is, how are the robots doing this? We're interested in the underlying mechanisms. Not just that they're doing it, that's fine, but we want to understand, because we're interested in artificial intelligence, we're interested in building robots. How do the robots actually achieve this, right? Now, maybe we can switch to Warsaw for some suggestions on how this might be achieved. How would you do that?
Okay.
If you had to build or design a robot, how would you do that? If you had to design a robot that actually has to achieve this task, maybe someone in Warsaw could.
Okay, so I ask our students to answer the question. We are in Warsaw. Okay, could you try?
Can I speak?
Yes.
So what I think that a robot, when a robot meets a particular cube, it starts to push it, and it pushes it until it meets next cube. So it connects somehow the cubes, put it together, and then snaps to push the cubes and looks for a next one to put all the cubes together. That's my opinion.
Okay, so basically it looks for a cube, and then looks for a cluster and moves the block to the cube, right? Cluster and moves the block to the cube. Okay, yeah. Move block to cube, or to cluster, and then basically you repeat this. Okay? Right, other suggestions? No, I think, Okay. Well, I think that's probably what we would think that how we would do this. Okay. Well, thank you very much. Now, of course, the advantage of building robots is we actually know how they work, because we programmed them, or we built them. Not only programmed them, but we built them, so we know how it works. Now, I'm going to show you how it actually works. So this is how they're This is what the robots are really doing. So if they have two sensors, one on the left and one on the right in the front, and when there is sensory stimulation, so these are very simple infrared sensors that very roughly measure distance. If there is sensory stimulation on the left, turn right. If there is sensory stimulation on the right, turn left. That's basically all they're doing. Now, right here, they're actually programmed for obstacle avoidance. And I put obstacle avoidance in parentheses, because, this is basically, thinking about frame of reference problem, right? You remember the frame of reference problem. This is the world from the perspective of the robot. It only sees sensory stimulation left or sensory stimulation right. It's not a very interesting world. It's not very exciting if you just have two sensors. And the obstacle avoidance, I put that into parentheses. Why do I put it in parentheses? Because this is our perspective as observers. The robots don't know that they're avoiding obstacles. They just turn away. They have absolutely no clue, right? Again, frame of reference problem. Okay, now I'm telling you that this is the way it works, but why does it work? Now, why do you actually get the clusters? That doesn't explain why you get the clusters. Okay, here's how it works. I'll go through this quickly because we're running out of time, as always. This is the explanation. If one of these robots happens to encounter one of the styrofoam cubes here, head-on, it doesn't get sensory stimulation here, and it doesn't get sensory stimulation here. So what happens? What happens? The robot will push the block, right? But basically it pushes the block not because it wants to push the block or because it's programmed to push the block, if you like, but because it doesn't see it. It doesn't even know it's there. Now, the question is, how do you get the clusters then? Well, as you would probably think, it depends on how far you push the block. So when this block is here, and there is another block here on the side, it will get, sensory stimulation here on the left, and then it will turn away. And now you already have these two blocks together, and then the probability that next time around you will have yet another block deposited near these two is increased, and so this is how, over time, you will get the clusters. Okay? This is cluster formation. And of course, you will always get a few blocks on the side of the arena. Right? Now, let's make an experiment. Let's leave everything as is. So let's leave the control program as it is, just this sensory stimulation on left, turn right, and so on. And let's leave the environment as it is. We take exactly the same environment. The only change that we're making is we're moving one of the sensors into a different position. So we're moving this sensor here over here, right? That's all we're doing. Nothing else. Now what happens? Okay, well, what happens is pretty obvious. There's no clustering anymore. Why not? Because as the robot now encounters this one, it will get sensory stimulation here, and it will turn away. So you don't get the clustering anymore. So mind you, we now have the same environment. We have the same control program. We only make a small change to the morphology, sensors, and, this part of where the sensors are positioned, that's part of the morphology. We only make a small change to the morphology, and the behavior is completely changed, right? That's should be, for a computer scientist, should be a nightmare. You have the same environment, you have the same program, but you have completely different behavior. Okay, now let me summarize this a little bit. We have the frame of reference problem. When we talk about obstacle avoidance, when we talk about cluster formation, about cleaning up, these concepts are all in our heads, not in the head of the robot. Actually, Dan Dennett, that was also mentioned by our friends in Munich. Dan Dennett, the philosopher, who gave this example with the... Dan Dennett said about these robots, well, these robots are cleaning up, but that's not what they think they're doing. basically, I mean, it was meant as a joke that, what they think they're doing in quotes is just avoiding obstacles. Okay. There is a close interdependence between morphology and behavior. So you change the morphology, the behavior changes. So that means if you, for example, want to understand the function of the brain, it is not sufficient to look at the brain itself. But you have to look at the brain, how the brain or a control architecture is embedded into a physical system and how this physical system interacts with the real world. And this is also what we call, this is extremely simple. You have to admit, the design of these robots is extremely simple. Just basically, obstacle avoidance, this reflex, primitive reflex. And then you get this cleaning up. So this is also what we call cheap design. So you're exploiting the properties, taking benefit of the properties of the ecological niche. You change anything in the ecological niche, it's not going to work anymore. You take away the boards on the side of the arena, the robots will just move out. You use concrete, a heavy material instead of the styrofoam cubes. It's not going to work anymore because the robots will not be able to push it. If you make the cubes larger, it's not going to work anymore because then this, pushing mechanism doesn't work. So it has to be exactly tuned towards, the particular ecological niche. However, and so you can say, well, it's very limited. Yes, it is. But in the real world, there is no universal agent. Universality is only in computation. We had computation last week. In the real world, you're always tied to a particular ecological niche, whether you're a biological system or whether you're a robot. Okay, and then the way this is achieved, we also call self-organization and emergence. We will have to say a lot about emergence in the future. Okay, and so one of the goals is that will be then in the 7th and 8th lecture, is to come up with a set of principles that characterize intelligent systems. And so over time, I will, explain all these principles. Here is a first one, just so that you see in which direction we're going. That's called the principle of cheap design. Cheap is kind of meant to be a bit of a joke because cheap also has a negative connotation. Cheap is no good, But the way it's meant here is as follows. First of all, it should be parsimonious. The model should be parsimonious, which means simple. If you have a very complicated model and a simple model, and both do the same job, the simple one is to be preferred. This is a principle that is also known from the philosophy of science called Occam's razor. Maybe some of you have heard that. Okay. Second point is we have exploitation of the ecological niche, meaning you take advantage of what's going on in the ecological niche. Okay? And the third point is you exploit the specific interactions. So you exploit the fact that you have this environment, then basically you don't need to take care that the robots don't go away, and so you take advantage of the specific interactions. Okay? This is the principle of cheap design. We will encounter that all over. You can think about natural systems, they all exploit this principle. Now, just for the fun of it, what we have done here is we've taken, if you, like here on the left, if you take a dish and you put into this dish, you spread dead ants into this dish, and then you add a few live ants into this dish. This is what the live ants will do with the dead ants. This is what the databots do with the styrofoam cubes. This is just for the fun. We're not claiming that this is a good model, that the databots are a good model for the ants. Okay. Now, just a question for the break. In about 5 minutes we're going to have a break. Just a question for the break. I'm not going to talk about this. Think about this. What happens if instead of 4 robots or 5 robots that we have used for the experiment, we only use 1? Okay? But I'm not going to answer that, and we're not going to discuss it here because I need to go ahead. Okay, now, so basically we've discussed this case study, but please, whenever you have a question, do ask the question or ask the question during the break. Then I'm trying to finish up this now. So we already had the Munich presentation, and now I want to come to the symbol grounding problem, which is a very difficult problem in artificial intelligence. Okay. And I will do that by using the so-called, symbol grounding by using having a problem with the smart board here. Help me with the smart board. I'm having a problem. I can't advance the slides here. I cannot advance the slides anymore. Okay. Well, anyhow, I will continue my explanation here. So what we're doing today is we're looking at, we take an example from Japan, I think a very beautiful example. It's a so-called, what we have here is a so-called karakuri ningyo. Karakuri ningyo is a mechanical robot. In this case, you see a tea-serving robot. So, so this is a tea-serving robot which was constructed, these kinds of robots were constructed during the Edo period, which was, I think, 1603 until about 1867. And this was a period of, it was actually a period when Japan was completely closed off from the rest of the world. But during that time, they accumulated a lot of wealth. And then for the purpose of entertainment, rich merchants, had these dolls developed. Now, I would like to show you how this works. So these were purely mechanical. And so there's no battery in there. Now, I have to wind this. I'm going to wind this, okay? Oh, there's a lot of winding to do here. And then I would like to give you a short demonstration of how this works. What this kind of... So, right. And as soon as I put some weight on there, it will perform its job. Let's see. So it's also very polite, It does the ojigi, Okay. Very good. Come here, please. Okay. Well, so I guess we've seen the karakuri ningyo. So now, what would I like to illustrate with that? So I think we're back in business with the smart board. So this is karakuri ningyo, and they're festivals here, like what you see here. People celebrate every year in some areas. There are performances. Here there are performances of these dolls. Here you see two examples. I just showed you one, and some people claim, like Kirsty Boyle, that Japan's love of robot lies in the history of the karakuri ningyo. So this is, of course, a hypothesis, but she did a very beautiful study, and there's a very beautiful website by Kirsty Boyle on the karakuri ningyo. And if you look at modern Japan, you see that there's really a tradition. You have the kind of Edo, the old traditional robots, and then you have the very modern robots. And here you have an encounter of karakuri ningyo with 21st century robot technology. We have already seen this demonstration. Here is just for your information a bit on the Edo period. And now what I would like to do just before the break is very briefly discuss with you how, if you had to design a robot. Now, mind you, we are into synthetic methodology. So synthetic methodology means building things, right? So we want to build things. And we hope that by building things, we will understand better. So you saw this robot, a tea-serving robot. Now, if you want to build a tea-serving robot, what would you have to kind of put into that robot, to make it actually work? I mean, of course, you can observe a human waiter, right? But the waiter, will do its job irrespective of whether you understand or not what kind of knowledge he is using, right? And what kind of devices. But if you have to build one, as in the synthetic methodology, then if you don't do it right, you forget something, it's just not going to work. I mean, that's kind of, the idea of the synthetic methodology. Okay, so maybe we can have, we can switch to Zurich just before the break. I don't want to take too long, but just a little bit. Let's switch to Zurich. And maybe Simon, you can take over, and you can give us an idea of what's involved in actually building a tea-serving robot. So, Maria, can we switch to Zurich?
Okay, so thank you, Rolf. So I asked the students about 1 hour ago if they would have some ideas about how to build such a robot. What are the important aspects of that? So maybe first of all, is there anyone who dares just think something about that, some ideas that pop up? Okay, as I can see, it's pretty quiet. Okay, but maybe, so what are the important points that you think we should think about when building such a robot? I mean, for example, where should it be able to work? Is that something important in your opinion, or do you have... Okay, so maybe I'm just... Yeah, okay, I think there's one person over there.
Hello, Rolf.
Hi.
I'm actually interested... Yeah, hi. I'm interested in the idea of having coffee in bed. And tea in bed. So I think in the morning, first thing to wake up. Thank you very much.
Okay, thank you for your comments.
But that's my
that doesn't make the problem very easy. Yeah. Okay. Coffee in bed. Man, pretty challenging here. Okay, coffee in bed.
Okay. Maybe I would have actually another suggestion, because I think trying to build a robot which moves around in a restaurant or at home or even going to your bed is something pretty difficult to achieve. But what about having, something like a tea throwing robot? So basically you put the tea in a bowl, which is tea throwing.
A tree what? A tea what?
Throwing. I'm going to explain.
I didn't understand.
Throw.
Okay.
To throw the tea. So basically you put the tea in a bowl, and instead of having a robot moving, you could throw the ball to some place and have another robot catching the tea. That would be actually much easier, actually, because we get rid of all the problems we have by moving. So I don't know, that's maybe also an approach that could be interesting. Okay, we have maybe another reaction there.
Okay. Interesting approach, yes. Thank you. Okay, so we have another statement, yes?
Another challenging approach would be to try to build a robot to serve tea in a train that's moving.
Yeah. Very interesting. There's a twist question. Yeah.
Moving train, yes. Moving train. Yes, very good. Excellent. Okay, we're getting here into challenging issues, Do we have other ideas? I mean, what if you were actually to build one, design one, what would the robot have to be able to do? Maybe I can write something. I mean, yeah?
Yeah, I was just thinking, the tea serving something quite Japanese. They have also a system to serve the sushis, which is actually quite a clever way of having, could be also considered as a robot. So basically you just have...
You mean the kaiten sushi?
Yeah.
Kaiten sushi-like. So to make it easy. To make it easy for the robot. Yeah, okay, exactly. Very good.
Because I think it's easier for the human... I think it's easier for the human to learn how to get the sushi than to teach a robot how...
So this is the conveyor belt.
Conveyor belt, yeah.
Okay. Yeah, okay, there's another.
I think there's another idea. The coffee must be held warm.
Yeah, that's
so it needs a heater or something like that.
Okay. A heater. I mean, maybe if you just have to serve it, then if you do it quickly, maybe the coffee is still or tea is still warm. But okay, I write down the heater. Yes, keep warm.
There's another suggestion.
Another suggestion.
I would have a suggestion for the coffee in bed problem.
Okay.
I would just program a coffee machine, put it next to bed, and let it pour coffee when I wake up.
Okay.
Thank you.
Coffee machine next to bed. Okay, yeah. Next to bed. Mm-hmm. Okay, I see you guys don't want to design an actual robot. One wants to design balls, the other one just take a coffee machine that exists. But I would like to build a robot. So you have to help me to build a robot. What about a camera? I think the robot needs a camera. Why does it need a camera? Of course, it has to see something in the environment, right? Okay, what else? Do we have a few more statements from Zurich? Otherwise...
there's one coming.
Okay, there's one more. Let's take one last one before the break, okay? Yeah, please, go ahead.
Okay, I think it would be nice if the robot would have the capability to add some integrants. So if you serve a tea or a coffee or something in a restaurant, you can ask the person who ordered it if he wants sugar, if he wants milk and everything. So some kind of interaction would be nice.
Okay, interaction. Okay, I think that's a very good point. Interaction. Here we have milk, sugar, etc. But do you also realize, I think this is an excellent point, do you realize that if you want to do that the robot has to be able to talk? It has to be able to communicate somehow. It has to recognize milk. It has to recognize sugar. It has to know what this is. It has to have the ability to manipulate that. So it will need ways in which it can manipulate the environment. It needs actuators. It needs maybe hands, arms, whatever. So all these things, and mind you, just recognizing these things is a big problem. So I think we have a good number of points here and some very original ideas. And I would like to thank you. And I think now it's time to take a break. Okay, so I think since we're a bit behind schedule, we should probably reconvene in about 15 minutes. Okay? So let's take a break here. Thank you very much. Feel free to ask questions during the break. Thank you.
Munich, can we check please again the second microphone? I think that the second microphone has still problems. So please, let us check again.
What, in Tokyo?
No, in Munich.
Ah, okay, yeah, good.
Ich denke, dass die Batterie zu schwach war. Der Techniker hat die Batterie gewechselt, das sollte jetzt eigentlich normal funktionieren. Kannst du mich jetzt gut verstehen?
Nein, also das Volumen ist immer noch zu tief und ich habe noch zusätzlich ein Feedback von deiner Seite. Könntest du das nochmals vielleicht ein bisschen anpassen?
Mit Mikro 1.
Das heißt, es sind zu
gut,
viele
ja.
drin, ja? Okay. So, 2 Einstellungen tiefer. Die Bässe sollten weg sein.
Also weißt du was, also die Qualität zwischen das Mikrofon 1 und 2 ist wirklich sehr unterschiedlich. Also ich würde euch empfehlen, zurzeit mit Mikrofon 1 zu arbeiten.
Okay. Ja,
also könnte der Moderator noch ganz kurz nochmals etwas sprechen? Ganz kurz?
Marc, kannst du was sagen, bitte?
Yeah, sorry, are you expecting something from me?
Wie ist das im Moment?
Ja, ist besser. Ist besser. Weißt du was, ich würde bei diesem Mikrofon bleiben. Also ich höre dich wirklich nicht gut, wenn du über Mikrofon 2 sprichst.
Okay. Aber Mikrofon 1 ist in Ordnung, oder?
Ja, das ist perfekt.
Ja, sehr eigenartig. Okay, wir haben exakt die gleichen Einstellungen, aber Mikrofon 2 scheint einfach von der Bauart...
Ja, also ich höre dich jetzt fast nicht. Also das ist...
Okay. Das heißt, Mikrofon 2 hat wirklich ein Problem. Technisch intern, denn die also die Audioeinstellungen sind exakt gleich bzw. angeglichen. Ich sehe das auch am Pegel, aber ganz offensichtlich kommt es nicht durch. Gut, nehmen wir das Mikrofon rein. Ich bemühe mich mal, dass die Technik mir noch ein drittes zur Verfügung stellt. Also wir werden ja wohl noch einen dritten oder vierten Mikrofon haben. Möglicherweise haben wir dann die Möglichkeit, wieder mit 2 zu arbeiten. Denn das Wechseln des Erstmikrofons ist nicht so günstig.
Ja, es ist zu leise. Also ich verstehe dich wirklich nicht. Und für diesen Anlass ist, glaube ich, nicht, dass empfehlend ist, diesen Mikrofon zu benutzen.
Gut, okay.
Danke dir, auf jeden Fall. Ja? Gut.
Ja, bitte.
Ja, sehr gut. Also wirklich, also auch die Audioqualität ist sensationell. Also auch schon dort gibt es Abweichungen zwischen dem ersten und zweiten Mikrofon. So we have still the background noise from your side. Can somebody just speak a little bit, just to let us check if the audio quality
I can
is
speak
good?
a little bit. Do you have this noise again? I really don't know what is it. Probably it's because of our electrical system here. We got 2 phases, and we connect some devices to one phase and some to another. Maybe this is because you have this noise. Do you have this noise right now?
Yes. But the audio quality is really perfect. I mean, we have.
What about now? I've disconnected all our devices. Do you have noise?
Yes, I just have it.
Mm-hmm. So.
Oh no.
Was there a noise before? Do you remember?
Just let us check again, because I think that we have also a local background noise at our office. Just 1 second.
So if anybody has questions during the break, please feel free to ask them. Okay. We're very lucky that our speaker has arrived.
So the background noise is definitely from your side, Warsaw.
I'll try to do another one.
Okay.
What about now? Do you have the noise?
Yeah, still the same. What you could try is just move around maybe laptops and other devices. Sometimes if the devices are kind of generating the noise in the other device, then it helps sometimes when you just move them around a little.
I really don't know, because we've moved all our devices off.
Oh, okay.
And it's still a noise.
Munich, do you hear also the background noise from Warsaw? Can you agree with us?
Wenn Warschau was sagen würde, könnte ich das nochmal bestätigen. Also ich habe einen leichten Brummen gehört gerade, ja. Ich habe mich zwar unterhalten, aber das ist wahr. Ihr hört mich immer noch schlecht, ich muss lauter reden, ne?
Ja, gerne.
Ja. Okay, dann rede ich einfach lauter in das Ding. Also im Moment...
Maria, what about now? Is it still the same?
Yes. Yes, it's about the same.
Würde ich auch sagen. Hört man hier auch.
Also, was ich jetzt nochmals mache, ist Warschau zu muten. Jetzt ist es weg. Könnt ihr das...
Richtig. Jetzt
ja,
ist es weg.
gut, okay. Ja, das ist definitiv falsch. Ja, mir sagt einfach das Muten zu muten. Ist gut? Okay. Warschau? What I would like to do is that what we can do is that we mute your microphone. What do you think? Or you want to just try to fix it local?
Do you mean that you have this noise all the time and also when we are not speaking?
Yes.
Oh, I didn't hear that.
I just try to mute the system because I would like to check if there's still the background noise from your side when you're muting.
I mute the system right
now. Okay. So there's enough when you mute your system, okay? Because when you mute, we do not hear the background noise. And what I would like to check for the next time, I considered to start again a test connection so that we can try to fix the local problem and to agree the audio quality.
Maria, do you mean test connection in meantime between this lecture and another, or before the lecture?
Now I have really problems to understand you. The audio volume is too low and also the background noise.
Yes, that's because I've tried to lower our volume of some kind. But I've asked, do you want to have a test connection between our meetings or before the next lecture?
Yes, that's correct. I will contact you by email and send you the date when I would like to make the test. Huh? Thank you very much. So for this lecture, I think we just have to mute, and then the other participants do not hear the background noise. Thank you very much, Warschau. Ganz kurze Frage nach München. Habt ihr das Autosystem auf lautlos eingestellt? Ist das korrekt? Könnt ihr kurz etwas sagen?
Ja, Test 1, 2, Test. Kann man mich hören?
Jawohl. Gut, danke.
Maria, this is Worto again. Do you have the noise right now?
Mm-hmm.
Yes.
And now?
Yes,
do you hear the noise?
Lower.
It's a little bit lower now.
So
but
I
it's
think
still there.
There is something with our wires. We will try to improve this for the next meeting.
Thank you.
Hello, Maria again. How about now? Do you hear the noise?
It's better now. I think that I can't hear it anymore. Just speak a little while.
Yes.
Again.
Yes, I can speak. I think we've
now
improved
it's
our
much better.
Mm-hmm. Okay. So we will stay without muting, okay?
Okay. Yes. Thank you.
Thank you.
Well, welcome back after the break. Now, concerning this design of the tea-serving robot, so what we see here is I think we have ideas at several levels. Of course, the first one, when you say, well, in a moving train or in a restaurant, or you want to drink coffee in bed, what you're discussing is really the environment or the ecological niche. And we will see what's called the ecological niche. We will have an assignment, a special assignment for the students in Warsaw for next week, where they should tell us a little more about the ecological niche. And I think it's very important, I'm glad that people made this point, it's very important that you never look at the agent alone, but that you always think about the environment in which it's going to perform. Because if you want to apply, remember, the principle of cheap design, you want to exploit the givens, what's there in the particular ecological niche. We'll hear a lot more about that. And, sometimes by modifying the environment a little, for example here, you make a modification to the environment, maybe the task becomes real easy. You just have people sit around, this bar with the belt. And then I think what you need to specify is, well, cameras, certainly you need to specify the sensors. You need to specify the actuators. You need to be able to manipulate the environment, right? And then here we had interaction. So this is basically, you need to kind of recognize things. You need to recognize that there is a human, that you want to interact with the human, that you want to understand something. So I think there are a number of points that I would like to extract from here. You can see they're at different levels. One is the sensors, the actuators, so the actual physics, the physical setup of the robot, which is something that we call the low-level specifications. But then this robot should be able to recognize, what is tea, what is a cup, what is a customer, what is milk, sugar, whatever. And we have these two levels. Now, the problem that we're faced with, if we have something like a cup, well, how does the robot recognize that something is a cup in the environment? So we have this concept of cup, and then recognizing the cup is a very difficult issue. And this is also called the symbol grounding problem. Now, we have what's called low-level, can't write anymore, low-level specifications. Low-level specifications. And we have level specification, and we have something that we call, the concepts, like tea, what is a customer, what do? You can serve tea, they have to pay for it, you have to supply ingredients, you ask them what they want, and all that. That's called this is low level, that's called a high level ontology. Basically, an ontology is all the concepts, the basic concepts that you're going to use in the environment. And now you can see immediately that what you're specifying is basically cameras and things like that. What you want the robot to recognize is things like, teacups and whatever, tea, customers. Now, but these, think about the frame of reference problems. These are the concepts, these are our concepts, of a coffee shop. These are not the robot's concepts. Now, it happens that our sensors are completely different from the sensors of the robot. And so, And we will see that all along because we have now different embodiment. Humans have a completely different embodiment from robots. The concepts that we will form and the concept that the robot, is basically are natural for the robot will be very different. So we're going to have the problem of, mapping what we're getting from a camera, for example, here, what we're getting from a camera onto these concepts, teacup. So the robot, gets a camera image. Well, how does it know what is a teacup? This is a very fundamental problem. We're going to talk about this all along. It's also called the symbol grounding problem. Symbol grounding problem. And to finish this up, so please read about this, think about this. I just want to get you to think about this. It's a very hard problem, very fundamental problem. 40 years of research in computer vision have not been able to solve this problem. Now here is what our friend Gary Larson, famous cartoonist, has to say about the problem. And here I think he's addressing the issue that things in the real world don't come with labels. So basically, how do you know it's a house? How do you know it's a tree? Things don't come with labels. Now someone's telling me, okay, and here is how Gary Larson would solve the symbol grounding problem. That's Gary Larson's solution to just label the stuff. But then, when I told this to Professor Kunyoshi, he said, well, what? But everything has a barcode. So basically everything now these days has a barcode. Now think about, I'm not going to discuss that here, but think about how life would be if you had kind of a sensor. Babies were born with a sensor for barcodes. And then you would grow up in an environment in which you actually always had, from birth on, a sensor for barcodes. And it's still a question how you would label the Japanese C with a barcode, or how would you, there's, a few issues that remain, but... Okay. So this concludes now the discussion of the fundamental problems. This concludes my discussion of Chapter 3. And we have already, made inroads into Chapter 4. And I would like now to study, so next topic is Chapter 4. Also the exercise that we're distributing today is about Chapter 4. This is about designing autonomous agents. We already started with the tea-serving robot. So let's now have a look at this. What I would like to do first, now also to get some interaction going, I think this has been going very well, and I would like to encourage you to also participate in discussion now. Very briefly, maybe we can switch now to Beijing, and you can give us perhaps an idea of what the term autonomy means. In all, good idea of autonomy, and since we're interested in designing autonomous agents, let's think a little bit about what autonomy actually means. Okay, so maybe Beijing can take over, and let's have a few thoughts on autonomy.
Okay. I think autonomy means independent from external control. And as an autonomous agent, it should perform emergent behavior.
Control. Okay, you mentioned emergent behaviors.
To perform such behaviors, it should be. I think the ability of learning is needed.
Okay. So autonomy would be coupled, in this view, would be coupled with learning. Okay, I think that's an interesting point. Learning.
And it's to be a result of the interaction with the environment.
Okay.
That's all.
Okay. Interaction with the environment. Do we have another statement from Beijing? Interaction with environment. Do we have another statement from Beijing? on autonomy?
Well, I think the autonomy means the agent or something can decide what he will do only by himself and not by the environment. I think this is the autonomy means. Thank you.
Itself or him, herself, huh? Herself, okay. Good point. Maybe one more. Do we have another one?
Well, maybe it should have the ability to make decisions, or it should have the ability to think.
Oh, ability to think. Okay. Ability to. Okay, very good. I think we'll leave it at that for the moment, right? Now, I think this is basically independence from external control, what we're interested in. Here, the idea about deciding by itself, that's a very tricky issue. I think it's tricky philosophical issues. Ability to think, we will have to kind of have a better idea of what we mean by thinking. Okay, what I would like to do now is just very briefly give you an example from technology. Of course, what we're interested in basically is building, autonomous agents. I would like to discuss with you now. Maybe we can use the ideas that the people in Beijing gave us about autonomy to discuss the Mars Sojourner. I'm going to go through this quickly. It was launched in 1996, and of course the landing, this is American patriotism, was on the 4th of July, which is the national holiday in the United States. So it landed on the 4th of July. And here is the robot, and this is the ecological niche. Also you always have to define as a pretty tough, pretty demanding ecological niche to design a robot for. And now we have a short video. Maybe we can switch to the video so that you get an impression of how this robot actually performs. Okay. Okay. Right. So now this is the Mars Sojourner just going down the ramp. Maybe we can switch quickly through these. They're not terribly interesting. Maybe we can switch to the next one. And here you see a bit of the environment. You can't see it very well. And these were not real videos that were taken, but these were kind of individual pictures, photos, and then they were compiled into an animation. So you see it's relatively rough and the quality is relatively poor, but these are authentic pictures from Mars. Maybe the next one. And here you see it turning. I think it's pretty ingenious construction that it can turn like that. But you have to keep in mind that this is 40 times the real speed. So a speed up of 40, and then it turns at this speed. So it's very, very, very slow, right? But still, it's turning nicely. Next, please. Oh, here we go. Here, I think this is cool because you can see the scoop. You see, there's kind of a shovel in the back because it has to get samples. Okay, yeah. Next one, last one, please. So this is the last one. This is just seeing it run into a rock. So there has to have means of kind of knowing that it's actually been running into a rock. It's not obvious for a robot that it's stuck, and it's stuck against a rock. You can think about that. Okay, well, I have the same videos, but I can't show them over the application sharing because... Okay, now what about the autonomy of the sojourner. Does anybody have an idea about the autonomy of the sojourner? Do we want to maybe hear what level of autonomy are we talking about? If anyone would like to volunteer here. Yeah, first statement. Yes, back there maybe. Oh.
Well, it has to have some degree of local autonomy because of the time delay between the Earth and Mars.
Local autonomy. Very good point. There is a time delay for a signal to travel from here to Mars of about 11 seconds. Is it 11 seconds? No, yeah. Is it 11 seconds or 11 minutes? 11 seconds. Huh? Minutes, huh? 11 minutes, huh? Yeah. Just confused. I think it's minutes. So there's absolutely no hope that you can remote control the robot. Remote control is not possible, right? So you could, of course, make it very slow, but that would be, very, 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 very slow. And so what they decided to do is kind of a compromise. So they have some local autonomy, as was mentioned, but then they tell the robot where to go. They say, okay, go there, and then they let the robot go. They don't let it go very far. Okay, local autonomy. Do we have other considerations on autonomy? Yeah.
I think, such robots should have defined procedures how to deal with certain object. So I think he has a kind of representation of few situations that he can cope with. And of course, and basically that's it. I mean, in each situation, one algorithm is applied. So it's like a thin set of situations, and so
situations and what to do in these situations.
Yeah.
For example, what to do.
See a tree. Right. I mean, see a rock. So I mean, just look around whether
or maybe collect samples.
Yeah.
Maybe collect samples. If you see a particular type of sand, collect a sample or whatever. Right? Okay. I think it's a very good point. So we have to define situations and how to react to these situations. Okay. Now, high level, low level of autonomy, I think that was already mentioned. It's a relatively low level of autonomy, right? So, as we see now, we don't have autonomy as it's either autonomous or it's non-autonomous, but it's kind of, a gradual concept, more or less autonomy. Also, it's interesting that It's interesting that autonomy is not really a property of an agent. Think about the following. Think about parents who have children, right? Now, the more the parents were almost coming to an end. Just the last example for you to think about. The more the parents know about their children, the more they know about what they have been doing, and the better, and the more they know about how the children react to external events, the better they can control the children. The less they know about the children, the less they can control them. And maybe an external person who knows very little about these children will have a very hard time to actually control these children. So with respect to one person, these children, or this child, may have very little autonomy, being easily controllable. With respect to another person, this child may actually have a relatively high level of autonomy because the person does not know how to kind of manipulate this particular child. So I think just one thought that I would like to give you is that autonomy as a relative concept and not a property of an agent. Not property of an agent. Okay? So it's a property of a relation, if you like, and not so much a property of an agent itself. Okay, now just to finish up, we're going to talk about so-called complete autonomous agents. And please do some reading. This will be available in electronic format. Of course, complete autonomous agent means that it should be autonomous. And obviously, it should be what? It should be embodied. Because we're talking about embodied agents. It should also be, and please read about this for next time, it should also be situated. And embodied, situated, and it should be self-sufficient. Okay. So please read about this. We will continue here next week. Now, what I would like to do now, something's wrong with the smartboard. Something's wrong with the smartboard here. What I would like to do now is switch to the last part of this lecture, which is a presentation. I think we're very lucky to have Professor Inaba of the University of Tokyo here, and Professor Kuniyoshi will briefly introduce Professor Inaba. So I will pass the floor to Professor Kuniyoshi. You can just stay there.
Thank you, Rolf. Today we have a guest speaker, invited lecturer, Professor Inaba. And Professor Inaba has been first working on intelligent robots which utilizes vision to realize intelligent manipulation and other behaviors. And then he created a new approach called the remote brain robots, through which he showed sort of groundbreaking examples of what kind of behaviors a robot can exhibit. And together with that, he's been investing a lot of effort in creating a software environment that is essential for pursuing highly integrated functionality for robots. Then recently he's working on, again, a very new approach in fusing morphology and also materials, exploiting such properties into a humanoid robot design, coming up with a very new design. And Professor Inaba has been known as a very famous and one of the world-leading researchers in robotics. So please start.
Thank you very much, Professor Kunz. Okay, I have time about 25 minutes. Today, I prepared this series of our research results so far, and I'd like to explain about a simple view which I look over my research history, and I'd like to talk about the modality of robot body. Next. Oh, here. Okay. Robot body has several modalities. Here it shows it unifunctional and task-oriented robot. It's the old robot. They are designed for the specific task. Manipulator, mobile robot, and robot vision is also robot. And another very new robot is the life form robot. The snake-like and the quadruped, dog-like and ape-like and the humanoid. And also that we can see other in IT-based robots, internet software agent. It does not have physical body, but they call it searching robot. So, and also the cyborg. It is integrated inside the living body with physical artifact. And smart space, like a room, is also called a space robot, a smart room robot. And also we are trying to build a new robot which can change its own morphology online. And I'd like to show our robots which we have developed so far, and based according to that history. That first is hand-eye robot, which did the rope handling. Rope is very flexible, so the robot have to have their vision. And next stage is we wanted to put their whole body like us to the mobile robot body. We adopted a new approach we call remote brain, which we do not place a computer inside the body. Then we can become free to design the whole total robot system. And also that we could design and develop the small size humanoid and the very complex humanoid. And the last robot was the new robot I'd like to show. And could you show that video? The first video showed the rope handling system. At that time, it was 20 years ago. At that time, robot body is very separated. The computer and the camera and the single manipulator is connected inside a single room. And also the computer is very low power. So the human robotics researcher have to write a program which observe the flexible object and try to move, verify its own motion and monitoring the flexible object through the visual processing. So that the manipulator have to know where is the camera and where is its own hand with vision, so that hand-eye coordination should be solved in this experiment. The robot have to observe and move and observe and move. At that time, computer power is very low, so that it's not a concurrent loop during that motion. So that, but it was 20 years ago. Now we can change the speed. And next, please. And this was the very small quadruped life form robot. This is designed and developed by a fourth-year university student. He developed 2 days. That robot do not have a computer on body. It has just 8 motors, and the control signal is transmitted from that computer outside, so that the robot student can design and develop that behavior program like that. And next, please. And this is also that quadruped, but we put the passive wheel under the body, then the robot can select its own behaviors, walking and growing like that. Then robot can have some capability to learn its own functionalities. And next, please. And we put the camera of that body, and we program some task to pick up the ball and carry the ball to the specified, visually measured goal position. But the sensor is just a camera, but the robot can utilize that camera as several sensors detecting the distance and orientation, so that it can recover its own failures like that. And this is another 2-armed and 2-legged, humanoid-like, human-like robot. But the first step was the using arms and legs to satisfy the specified goal. In this task was the climbing the ground. The robot can observe its own orientation through the vision. The robot is programmed a very simple function, moving arms and legs and changing the orientation of its body. Then the robot can climb any slopes, the straight or curved. The robot can perform the task. Okay, next slide, please. And this is the standing, the similar ape-like robot. In this case, the robot tried to observe the swing motion, and after that to control its own body to accelerate the swing. And this was also the remote brain wireless signal link. It's the key for this dynamic motion. Okay, next slide, please. And also this is the first biped action. If put some sensor to detect the situation of its own robot orientation, then we can add some capability to recover its own robot situation like this. Next, please. And this is another locomotion style with arms. That in this case, that robot have to observe its own body motion, and also that there are horizontal bars, and so robot have to decide when its own arm should be moved. But in this case, the robot has a camera, and the robot camera can observe the optical flow and verify the grasping of the bars. Next slide, please. And this is a new robot that we can change that passive remote-controlled whole-body robot to that sensible body. The actuator become a sensor, so that in this case the human operates the humanoid, then the robot observe that operation, and the other 3 robots follow that controlled postures. Okay, next slide, please. And this is the recent action that in this case that robot have to coordinate that arms and legs. Also that wire computer is remote place.
Are these in the eyes? Are these 2 cameras, or is
this 2 cameras? Yep. Yeah, that's right. Okay, the next video, please. And this is the backbone environment. That computer system, every year we can change and growing, and we can extend the performance. So that this is the recent result. Inside the robot brain, the robot can simulate its own decision and environment dynamics and its own body and visual processing. So this is show that our robot brain performance. And now robot observes that environment change, then a robot have to find its own way during that achieving that some specified goal, picking up a pole in this case. And next slide, please. And this was the same action of the brachiation, but the robot body is very rigid, so that it looks strange, no flexibility. So we wanted to put some flexibility inside the body. Next, please. So this was the first prototype. So the torso has the flexibility that some spring-like torso. Okay, next video, please. And we wanted to extend that kind of flexibility like this humanoid behavior. So this was the actual 3D design of our robot, real robot. Next video, please. And this was that real one. So we could put more than 100 motor-based muscle tendon system, but it also has 40 muscles, and it has 10-segment spine in the torso. So this motion is pre-programmed by human, but the human have to solve that, how to identify its own robot configuration through its own sensors and actuators. So next slide, please. And this shows the flexibility of the complex body. During this motion, robot have to observe every sensor, or the robot just rigid, so that you see that robot can adapt, accommodate to that human operation. That it means that every muscle are controlled through the force sensing, tension sensors. So, next slide, please. And this is also that our brain system can build some image of its own image training space. And after this training, the robot, next slide please, this was acquired vision-based controller inside that robot brain computer. And next slide please. And this is another, the last modality of that robot body. You see that legs are special material inside. We are using low melting point metal into the leg. We can control that hardness of that metal. Then we can adapt its own body form to that environment. In this case, that four-legged robot can walk on the flat ground, and when it meets that ladder like that, then that robot tries to change its own leg shape using that temperature control. And in every leg has a heater inside, and the robot can control that temperature of that metal. Then robot select its own motion for any environment. This case, this was the first experiment done by the master course 1-year student. He designed this robot and built and programmed and did this experiment. Now he's a PhD last year student. Now he's writing his PhD thesis. That's right now. And he had to put more very complex and very high-level function, like planning and recognition function, and motion control and identification function inside the robot brain. I think that if we can build this robot as a very autonomous robot, then we can say that many aspects of the robot function that's almost solved. But right now, this experiment is controlled by human. The human make a plan how to use the legs and how to move its own legs. So the dream and the current state is very big gap we have. Okay, this is the last. Okay, thank you very much. And I just show the last slide. Just one comment. We built that spine and ribs and eyeball using the laser powder sintering system. We can build a free form body part, and this is the torso and the free form. We can crying. This is the last slide. So I have shown 4 different robots: task-oriented robot and live form robot, and other new modality, metamorphic robot. Thank you very much.
Okay, well, thank you very much for this presentation. Do we have any questions from any of the sides to Professor Inaba at this moment? Questions?
Yeah,
to Professor Inaba.
Can we have the question from Warsaw?
Okay. Go ahead, please.
Yes.
I probably haven't listened much carefully about the metamorphic robot. I'm wondering what's the feedback controlling the changing the metamorphosis of the shape of the leg. I mean, is it the camera that controls if the shape taken by the leg is proper, or is it maybe some kind of tensor?
Yes. That point is a very important point. So that first robot which I have shown did not have any sensor, but that was about 4 years ago. So right now we are trying to put another sensor to observe its own body. But you know that humans do not have the eye to see that our back, so that there is a limitation to observe. But you see the octopus can move and can survive any environment, so that we have to solve that kind of functionality with not only sensor-based, but also that some another behavior-based or the memory-based or something. So that is the current interesting topics, I think.
Okay, do we have, I think we have time for another question. Do we have a question from any of the sites?
So I think we have a question here in Zurich.
Okay.
We're going to
please
on this person.
I would like to ask about most of the navigation and recognition is based on vision, and I'm wondering what kind of explorations have been made in more touch sensitivity in terms of recognition and navigation.
Touch? Tactile?
Tactile, yes.
Navigation? Tactile
for navigation, yes.
Yeah, very important. On the video, I just showed the vision-based, but when we want like to build a tactile-based navigation, then we need distributed sensors on body, so that about 8 years ago we designed a new sensor suit. But whole body suit-like sensor suit, but the problem is how to utilize that information all over the body to navigate. That is the current and long way task, I think. Is that the correct answer to you?
Yeah, I mean, rats, for example, can use whiskers also for navigation.
I see.
Right.
Yeah.
Okay, well, I think we probably have to come to a close now. I would like to thank again Professor Inaba for an excellent and instructive, inspiring, and entertaining presentation. So thank you very much.
Thank you.
Okay, now I would like to... Okay. Okay, now I would like to just draw your attention to two things. One is, maybe the students in Warsaw haven't seen that yet, is that we have a frame of reference competition. The frame of reference problem, if I forget to mention the frame of reference problem in one of my lectures, anyone, the first person to detect that I forget mentioning it can choose either, a bottle of champagne, French champagne, supposed to be the best in the world, or a box of delicious Swiss chocolate. Some people say it's the best in the world. I personally prefer Belgian chocolate. But so whenever you detect that in one of the lectures I forget to mention the frame of reference problem, so please let me know, and then you can choose between these two. Okay, then last thing. Please read Chapter 4, which will now be available in electronic form, Exercise 3, and then we have a special assignment. And if maybe our friends in Warsaw can take care of that, which is a short presentation on the concept of ecological niches and how these concepts apply not only to natural systems but also to robots. And you can maybe draw some inspiration from David McFarland from Oxford University, who is one of the leading ethologists in the world. And he is also, I think, one of the people who started this idea of what he called animal robotics, so building robots to understand animals. Okay. Well, I think that's it for today. Thank you very much for your attention, and see you all back next week. Thank you. Well, if you have any questions from any of the sites, please feel free to ask. But the official part of the lecture, is now closed. Thank you.
I will have the question concerning the quality of the